Hello, everyone. Welcome to IE 4530 Manufacturing Systems and Techniques, Fall 2022, session E4 Advanced PLC Programming Part 2. This is the fourth and the final session of our module E, which is Programmable Logic Controllers. Last time we talked about some of the more advanced PLC programming instructions, such as timers, counters, move label, jump label, etc. Today, we are going to implement some of those advanced instructions to program a complex bottom line simulation model. As I mentioned that in class, this is a relatively more advanced PLC programming exercise, and I believe this video recording would be very helpful for you. The last assignment in this course, the second PLC programming assignment for you, would be to recreate this simulation model in LogixPro and basically implement the program that I'm going to be demonstrating here. Feel free to program it your own way if you want to try different ways of implementing some of the logic as discussed in class. Some of the logic could be programmed in many different ways. But if you want to just follow along and implement what I am going to show in this tutorial, feel free to do so. The specific instructions besides examine if closed, examine if open, and output energize are going to be timers, timer on delay, reset buttons, counters, move, some comparator instructions such as equal, less than. Some math instructions. In this case, is going to be conversion between BCD, conversion from integer to BCD binary coded decimal. I'll explain in the tutorial why we need that. And last but not least, we are going to be using shift register instructions, BSL, bit shift left, which is, you will see that this is a very powerful way of using PLCs and very simple on-off switches and sensors to implement very complex, relatively complex logic in using PLCs and ladder logic. At the beginning of this module, I mentioned the importance of PLCs. You have already seen it in the CP factory. You will see it in our final lab, in the PLC programming lab, which is going to be after Thanksgiving. That the integration of different stations, different processes, different machines, different robots is done using PLCs, a network of PLCs, each of them in charge of one cell. For example, the branch base module that we have in the lab is the PLC of that module is in charge of controlling the branch, communicating with Robotino, communicating with the FANUC robot, communicating with the CNC machine and the laser engraver. So that's a good example of a PLC sort of overseeing different silos of operation, silos of automation, and basically integrating them based on one like unified logic that the programmers program into that PLC. And that's it. Again, we already talked about discrete control. And here in today's example, it's a simplified, it's a cartoonish example, but it's a very powerful example for you to see the role of PLCs and how to use a PLC and ladder diagrams or different other languages. I mean, in this course, we only talk about ladder diagrams to control and to execute our intended logic using the PLC. All right, from this point on, I will be talking about the tutorial. Let's first spend a few minutes to introduce this simulation here in the slides, and then after that, I will switch to the software and continue the tutorial from that point on. But you have everything documented in the slides that are posted on Canvas. This bottom line simulation is a production line that has three main conveyors. The main conveyor is controlled using this this motor here, very similar to the silo simulator that you're already familiar with and we used in our basic PLC programming exercise in class. So the way it works is that this main conveyor moves this conveyor, the main conveyor, this motor moves the main conveyor from left to right. And here you have a number of limit switches that are responsible for detecting different properties of these bottles. We have two different types of bottles, small bottles and large bottles, and some of them are intact, but some of them are unfortunately broken. So the process goes as follows. The bottles enter this production line from left to right. And what we want to do is that we want to identify the size of those bottles, the existence of the bottles, the size of those bottles, and also to find out whether the bottles are broken or not. And then if they're not broken and they're large, we want to fill them with this orange liquid, which is filled using this large fill. And if they're small bottles, we want to fill them up with using this small fill valves, and then the liquid is dark blue. And here we have a fill tube. So we want to identify again not the type of the bottle, which is like if it's a large bottle, we want to fill it up with the orange liquid. If it's a small one, we want to fill it up with the blue one. And if the bottles are broken, we want those bottles to be skipped. We don't want to fill up any broken bottles, and we want to discard them through this this slot here. We want to discard those broken bottles, and then here we have another motor with a grinder that is there to grind those broken bottles and then dispose them into these boxes. The boxes on the scrap conveyor have limited capacity. I mean, it's up to us. It goes up to, I believe, 12, but it's up to us. Like reduce that number to 8, 10, however many we desire. And then we want to program this system, this lower conveyor and the motor here, such that it is energized and removes those boxes and brings the next box below this grinder to continue the operation. And here, the only thing that we have is that we have a sensor right here. I'll talk to you about that in the next slide. But in the main conveyor, we have limit switch 1, which is there to detect the existence of the bottle. So every time that limit switch senses a bottle, it goes from false to true. Okay. The second one, limit switch 2, is there to detect the size of the bottles. If the bottle is large, it turns green, true. If the bottle is small, it doesn't detect anything and it remains false. So 1 when it's large and 0 when it's small. And here we have the third limit switch, which detects whether the bottles are intact or broken. Okay. I have limit switch 4, which is the sensor associated with this field tube that I have here. That's an output to be energized, and this is the sensor associated with that. I also have L5 and L6, which I believe I have in the next slide, associated with these large field and small field tubes. We also have a cap ram. So once the bottles are filled up, we want them to be capped using this cap ram. Here I have LS7, which is the sensor associated with the cap ram. And this cap ram is there to, that's the output to be energized to basically cap the bottles. And this is the PLC on the wall. As I mentioned, we have a scrap conveyor. We have LS10, which is the sensor associated with, that is used here to detect the existence, to detect the box, whether the box is present or absent. It's very similar to the proximity sensor that we had in the previous slide, in the previous tutorial. And here we also have a counter. We want to use this display to count, to show the number of these bottles, small bottles, large ones, scraps, and also the number of boxes used. So we need to use counters to project those numbers. And then I did not have it in my previous slide. We also have some other limit switches here. We have, oh, I believe I skipped over that. So here we have LS5 and LS6, limit switch 5 and limit switch 6, that are the sensors that turn on again when the field tube is energized. We have LS8 and limit switch 8, which again, similar to the previous ones, is energized. It is turned on when the output is energized here. I have the scrap gate, as I mentioned. We have the grinder. And then here we have a divert gate, which is used to divert the bottles to this divert conveyor. Okay, so that's an overview of this bottle line simulation. And we want to go, again, we will review this process. We will break it down into specific steps to be followed, again, from starting the system, getting started. I'm going to break the video down, break the tutorial down into a number of steps for us to program this overall logic. So the very first thing we need to do is to turn the system on and use and create a sealing circuit to turn the system on and leave it on, and then be able to control the on and off, start and stop the system, very similar to what we did in the silo simulation. The next thing that we need to do in the tutorial is going to be to enable a stop and go movement, because everything that happens here is going to happen in periodic stop and go movement. So we want the system to move, we want the conveyors to move and stop between each of those steps. That is going to be like the size of like the distance between two bottles, for the sensors to detect them, for the scrap gate to discard the broken ones, for these for the fill tube to fill them up, for cap ram to cap them, and also for the divert gate to divert them to the divert conveyor. So getting started, enabling stop and go movement, and then we want to then use bit shift left to record the LS2 and LS3 recordings, these two sensors, for us to detect the type of the bottle and also the condition of the bottle, to then use that logic, that information later on for filling, discarding, capping, and also diverting the bottles. We want to program then to the fill tube to fill up the bottles. That's the next step. The following step is going to be capping the bottles, discarding the broken bottles, grinding the discarded bottles, separating the large bottles and small bottles, and moving the scrap boxes away from this conveyor. And lastly, we want to, as I mentioned, count the number of small bottles, large ones, scrap ones, and the number of boxes used. Let's get started. This is the bottle line simulation in LogixPro 500. And as I've already explained it to you in the previous tutorial in class, the simulation environment, here you can open the simulation by clicking on Simulations and Bottle Line Simulator. And as I explained it in the slides, and as you already know, if you hover above any of these items in your simulation, LogixPro gives you the information about their name and also their addresses. Here we have, I believe the first one is start. The first one is stop, I column 1/0, normally closed push button. This one is a normally open push button, similar to what we had in the silo simulator. And then the rest of them, we have the run light, which is an output. We have 3 different types of modes of operations. We won't be using them in this tutorial. But the rest of them, again, in case you wanted to know exactly what the address for each of them is, just simply hover above those and then those sensors and actuators, inputs and outputs to get that information from LogixPro. Okay, so here we have these sensors. You see the sensor is on now. This sensor is off because there's a small bottle underneath it. We'll run the simulation momentarily, and then you will see how through the data table and also through like the changes in the colors of these sensors, you will see what each of those sensors does. And then this is, here we have 2 gates. We have a scrap gate to discard the broken bottles, and we have a divert gate to divert the large bottles to this divert conveyor. We have a divert conveyor motor here, a scrap conveyor. These are outputs, and also the main conveyor in the system. We also have a cap ram, which is an output. These are all just visuals. This is the output, and this is the sensor, LS7, that tells us whether the cap ram is activated or not. Here I have the field 2 output O column 2 6, and then the input associated with that I19, and I also have 2 a large charge and a small charge. Large charge is for filling the large bottles, and this is for small bottles. Okay, the very first thing we want to do is exactly the same as the very first step that we did in our previous tutorial. We first want to turn the system on. In order to turn the system on, you already know that we need to create a sealing circuit here. So what I need is examine if close and output energize. I can also use latch and unlatch. In the lab, you will see an example of latch and unlatch, but in Siemens language, which is S and R, but that's basically the same concept, latch and unlatch. But here we want to use a simple sealing circuit. Start. That's my start, stop, and run. I also want run as an input here. And for your assignment, please make sure to label all the inputs and outputs. This is my stop, and this is, okay. Now, if you download this and run it, you turn the system on and off. That's the first step. In the following step, we want to enable a stop and go movement. But before I continue, I'm going to briefly explain what we mean by that. In the previous tutorial, in the silo simulator, we really didn't need that stop and go movement. The only time that we wanted the conveyor to stop was when it actually, the proximity sensor sensed the box below that solenoid valve. In this case, unfortunately, that is not going to work for us, because if I, similar to the previous one, if I create here now, if I create an examine if closed here, and this is the main conveyor, which I'm going to call main conveyor here, because we have 3 different types of conveyors. What happens is, if I download this and run the PLC, run the program on the PLC, the system is going to be constantly running, but that's not what we want to do. We want the system to function in a stop and go fashion, meaning that we want the system to, the conveyor to move and stop, then move and bring the next box and the next bottle and stop, and so on. Unfortunately, we don't have, I mean, the easy solution, the easy fix for it, for this would have been to put a proximity sensor somewhere to sense the bottles, and then we like program it like the same way we did it with in the previous tutorial for the silo simulator. But the system is only equipped with three, I mean, the main conveyor is only equipped with three simple limit switches, LS1, LS2, and LS3. And as you can see, LS1 senses the existence of a bottle. So it constantly goes from red to green, then red to green, and so on. This one turns green, which means like goes from 0 to 1, or from false to true every time it senses a large bottle. And this one goes from 0 to 1 when it senses a broken bottle. Okay, but this is not going to work for us. We don't want a continuous movement here. We want to program a stop and go movement. And I'm going to show you how to create that stop and go movement next. The next thing we want to do is we want to program a synchronous stop and go movement for the conveyor to stop, again, as I explained, for each bottle to be scanned for in terms of its size, its the condition of the bottle, and also if it's good, we want to fill it up. So we want to make those stop and go movements for the whole system to continuously move and stop the next bottle to do the relevant processing here. Now, in order to do that, what I am going to do is that we are going to make some revisions to our program. Now, the system is on. We want everything to happen, again, take place only if the system is on. Now, instead of energizing the conveyor directly, I'm going to be reading LS1 and then using it as another condition. So what I'm going to do is that I'm going to program a stop and go movement process for this conveyor, where the gap between each movement is going to be 1 second. Again, this we know in advance, but again, depending on the type of the operation, we may actually need more time. But I'm going to add 1 second delay between each movement. So the system is going to move and then pause for a second, and then move and then pause for another second. Okay. And the way to do this would be using a timer on delay. I'm going to create a timer here and name it timer T40. And then because we need a 1 second delay and the time base is 0.1, I put 10 here. So every time my system is on, every time the LS sensor, LS1 sensor, this one, that again senses the existence of a bottle. Every time this sensor goes from 0 to 1, which means there is a new bottle in the system, we want to start timing using this timer. And only if the timer is done, we want the system to continue its movement only when the timer is done. So you already know how to do this. Timer T40/DN, which means when the timer is done, then we want to energize this motor, which is our main conveyor. Now, if I download this program here to the PLC, I've already reset the simulation, and turn it on, the system is going to make stop and go movement. So you see, each time there's a new bottle, when the system is on, every time the LS1 sensor senses something, it starts this timer, right? And the conveyor is energized only when the timer is done. right? And then the conveyor is energized until there's a new bottle, right? And then when there's a new bottle, this LS1 switching from true to false resets the timer. And that's how we already know that. I mean, if I use, for example, a retentive timer, that is not going to work. But because like when the next bottle moves, you see the logic goes as follows. The system is on. When the LS1 sensor senses the next bottle, the timer will start timing, right? The conveyor is off. And then when the timer is on, the timer is done, that is going to energize the main conveyor. And energizing the main conveyor is actually going to move that bottle away from this sensor until it senses the next one. So during that time, we reset the timer, and then we will then restart timing when the new bottle arrives here. So that's the logic, again, that we implemented here. And again, the design of this system is, the system is designed such that we have the distance, the gap between the different operations is exactly a multiple of those, like the number of bottles. For example, here I have 2 bottles away, 2 bottles away, 2, 4, 5 bottles away. We have this, etc. Okay. Now we need to record the readings of LS2 and LS3 sensors, these 2 sensors, in order to then use those values for taking future actions down the line. In order to do that, we are going to need a bit shift left instruction. And I'm going to show you what we mean by a bit shift left instruction in this step. In order to create a bit shift left instruction, okay, the next step for us would be to record LS2 and LS3 readings in order to then use the values of those sensors down the line for taking future actions, from filling the bottles, the good ones, discarding the broken ones, capping the bottles, and also diverting the large bottles to this divert conveyor. Okay. In order to do that, we are going to need an advanced instruction called bit shift left. Shift register, in this case, we are going to use bit shift left. Again, the concept, once you've understood it, the concept is not that complicated. What we're going to do here with bit shift left is that we're going to use the recordings of these 2 sensors, and then use those recordings. Like each time this LS1 sensor, like it's the logic in simple terms is as follows: that every time the LS sensor senses a new bottle, that means everything has been shifted 1 bottle to the right. Okay, so every time a new bottle arrives in the system, if I go ahead and simulate and run the simulation, run the system again, you see every time that this bottle, this sensor senses something, sensor LS1, everything, all the bottles are shifted 1 bottle to the right? And then the bottle that used to be here, like 2 steps later is right here. Then 5 steps later, this bottle reaches the fill one, and then 9 steps later, it reaches the discard, the scrap gate, etc. Okay, and then bit shift left allows us to keep track of those bits. Each of these sensors contains a bit, right? For example, this one is 0, now it's 1, 1, 0 again, 1, 0 again. And then these values that this sensor senses could be recorded using a bit shift left or shift register instruction, and then used down the line. And why do we need that? We need that to then, for example, let me pick one of those. think about this large block, right? This recording could be used then down the line to here to then communicate to this field tube that this is a large one, and then communicate to this scrap gate that this is not a scrap, right? And then for this one, it doesn't matter. It caps both of them, the cap RAM. And then we use that information, that bit of information here to then tell this divert gate that, hey, this is a large bottle. You need to open the gate and move it to the divert gate, okay? And the way this works is as follows. Let me show it to you in action. Bit shift left is, as I mentioned, is a relatively advanced instruction that could be found under file shift and sequencer. And the first one is bit shift left. Bit shift right is the opposite of bit shift left. And it's an output. You see, bit shift left contains a number of inputs that need to be entered here. The most important one is this binary file address. I will open it in the data table in a minute to show you what that is. We need a control. In this case, we said the control data type R6 is the control data type, and then choose one of those numbers. The bit address that I'm going to be recording here is going to be, for the first bit shift left, is going to be this sensor. So as we said, we want to record LS2 and LS3, right? I'm going to use the first bit shift left here to record LS2, which is I17. And I want the length of it to be 32 bits. So let me open this data table and tell you what I'm talking about. We have different types of data. In this case, we have a binary data. And the address that we used for this bit shift left instruction was B31. And B31 goes from, this is the first bit of B31. So it's like B31/0, then 1, 2, 3, 4, all the way to 16. And then I have the next one. So when, which is like B32, B33, etc. Okay. So this is B3. This is a binary, a 16-bit binary input that we have specified here, B31. And I'm going to energize that using an examine if close. And the examine if close is going to be my LS1 sensor. So what this wrong means is that every time LS1, this condition goes from false to true, we energize bit shift left. And bit shift left, what happens in bit shift left is that it takes the value of this, this bit, saves it, and then shifts everything else to the left. So when I open the data table, for example, what happens is every time LS1 senses something, goes from 0 to 1, every time this wrong condition goes from false to true, that energizes the bit shift left. And what happens is that that bit shift left instruction is going to take the value that we have specified here, which is bit address I17, which is this sensor, right? Save it as the first bit and then shift everything else to the left. Okay, so it's, for example, it's going to save the next value of this sensor. So next time this there's a new bottle in the system, bit shift left is going to save this value, in this case going to be 0, for example, put it right here and shift everything else that existed in this line to the left. And then the beauty of this is that by shifting everything to the left, we are actually in the actual production line, we are shifting everything to the right, right? So I can use, then down the line, I can use these values down the line. So I know that this value used to be here 10 bottles or 11 bottles earlier, right? So 11 steps, 11 step, in this case, stop and go step right here, right? So here we're actually creating some form of a memory for the system to remember that like 10 steps before, was it a large bottle? Was it a small bottle? Was it broken, etc. Okay. So that's for the LS2 sensor. And I'm going to create another one of these because we said we want to record both LS2. So I'm going to name this. Unfortunately, I cannot name it, right? No, I cannot name it. But you already know what this is. I'm going to create another one for LS3. But because I've specified 32 bits, let me also explain this, why we have 32 bits. In shift register, again, I will run the simulation and then you will see it in action, and that way I think would like clarify it completely for you. I have put 32 bits, and what happens is that every time a new number comes, a new value of I17 is entered here, it shifts everything to the left. But if I put 16, that is going to go all the way to 16-bit, and then after that, discard the rest of them, right? It's like you can think of it as a train that only has 16 cars. In our case, our train only has 32, which means it shifts everything to the left. When it gets to this point, it then shifts them to the next line. So it borrows some of those bits from B32. If we define B32 as another input that is going to mess everything up. And that's why I'm going to use B33 for the next one. So it's going to do the following. It's going to move everything, shift everything to the left, and then shift them again to the next line, shift them to the left. And then when they get to this point, it's going to get rid of them. And the reason we have 32 is that we have a lot of bottles in this line, definitely more than 60, but less than 32 in one, that the gap between this sensor and the rest of the important places here on this production line is less than 32. And that's why we don't need, here we have the numbers actually, 24, 23. So if I hover above them, it should give me the number, right? 3. So this is the first one, second one, third one. This is the 25th one, etc. So that's why I put 32. Now, similar to the other one, we are going to create another binary, but again, make sure to put 3 or some other number, but don't put 2 because here we have 32 bits. The control should also be different. So R6, 1. You don't need to worry about this at this point because this is an advanced kind of like foreign address format. And then what I'm going to record is this input, which is I18. /8, and the bits are going to be 32. Okay. So that way we should be able to, using this bit shift left, these bit shift left instructions, we should be able to then record those inputs and move them forward. When you reset the data, when you reset the simulation, make sure, just double check, make sure that these values are not 0. Sometimes it zeros them. Now let me open the data table and show you what this means in action. Let's first pay attention to B3 1 and 2. When I run the simulation, you see at the beginning, all the bottles are small, are 0. All the bottles are small bottles, right? This one is B31 and B32 are for the size of the bottles, because here we are recording this sensor, LS2 sensor. And look at the LS2 sensor and also the numbers that you see here. Let me move it below this so you can see it. So every time LS2 sensor is 0, it's 0, 0. Now the next one is going to be 1, 1, then 0, then 1, then 0, 0, 0, 0, 1. I'm talking about this sensor. And you see, this is the latest reading of LS2 sensor, which is this sensor. So it reads that one, overwrites this value, doesn't overwrite, it shifts everything to the left and writes that latest value of that sensor. And then it's like a train. It moves, you see these two ones, now they're going to move to the next line, then the next one comes. So it goes like this, it goes like a snake. It goes to the left, and then they go to the next line, they go move all the way to the left, and then at this point, we just discard them because we reached that length of 32. So that's for the first bit shift left. Again, first bit shift left, we say the address is V31, okay? And then we record I17, which is this sensor. And then it records that value right here in the first bit of that address and shifts everything to the left. You see, everything is moving to the left and then to the next line and then gets rid of them. Similar to that, we have V33, and then the address is I8, which is the broken bottles versus non-broken bottles. When bottles are not broken, it's 0, 0, 0. Now let's wait for a broken bottle to arrive. And as soon as a broken bottle gets to this point, this value will go to from 0 to 1. A new one is coming, look at that. And this is the value that is going to be 1 now. You see, this is this one that is moving to the left. Look at the mouse pointer. That corresponds to this broken bottle, right? And that way I should be able to, if I stop the simulation and open the data table, I should be able to keep track of this. Look at that. This is the broken bottle, right? And this is which broken bottle? It's this broken bottle. So I know exactly where that broken bottle is, right? And then 2 steps before that, I really had to, I mean, that's what we're going to do next. Let me run the simulation again and pause it right exactly when the next broken bottle gets to this grab gate. Now, look at this one. This one right here is this bottle, because this used to be right here next to this 9 steps ago. So now I know that this is the value that I need to communicate to this grab gate, and that's what we're going to be doing next. That if this value is on, right? If this value right here is on, 9 steps later, we want to tell this grab gate that, hey, if this is on, if this address is 1 instead of 0, open. Otherwise, stay closed. That's the meaning of bit shift left and why we need bit shift left. And we're going to use the exact same logic here to cap the bottles, fill the bottles, and divert them to the divert conveyor, as I'm going to explain next. The next step is to fill up the bottles, right? We have already created stop and go movement. We already have these bit shift left, bit shift left, 2 bit shift left instructions for these 2 sensors. Now, the next thing we want to do is going to be filling up the bottles, right? In order to do that, I need to create a new rung, as you already know, because now filling up the bottles means energizing the field tube, right? And every time we have an output that has its own set of inputs, I need to create a new rung. So let's first create the output. Let's first create the field tube and then talk about the conditions that we need. Field tube, that's the output. Now, in order to energize the field tube, right? In order to open the field tube, I only want the field tube to open during that 1 second interval that I have. Okay, during that period, I want the field tube to open, and then I want it to close like slightly before that, a few milliseconds before, a few milliseconds after I stop the conveyor, and a few milliseconds before I then move the conveyor to bring the next bottle. In order to do that, you already know a powerful tool in comparators called limit test. You already know that the limit test tells us it goes from false to true when a value is within a certain range, right? And the value here for us is going to be what? It's going to be the accumulator value of our timer is 0, right? The accumulator value of our timer. And what I'm going to do is that instead of leaving it open for the entire 1 second, I'm going to put some more like stricter lower and higher limits for it, just to be conservative, but you can change these numbers and see what happens. So what is going to happen here is that I'm going to like every time the timer is timing, and then the value of that accumulator value is between 0.2 and 0.8 second, we are going to energize the field tube. That means you're going to open the field tube and fill up the bottles. Now you see we have this sensor right here, right? And that is going to, every time I open the field tube, that sensor is going to go from 0 to 1. That sensor is going to be activated. Now, we already know that we have 2 different types of bottles, right? We have the small bottles, and we have a small bottle, and we have a large bottle. What I'm going to do is that I'm going to then use that LS4 sensor value, which is LS4, which is the field tube. Again, every time the field tube opens, that LS sensor goes from 0 to 1. I'm going to then tell the system that if it's a large bottle, open this one. If it's a small bottle, open the other one. And here you see the very first use of bit shift left and bit shift, bit shift left and shift register in general. So here I have 2 options, right? Every time this opens, that means this field tube is open, and the field tube is going to expect a charge from one of these outputs. It's going to expect one of these outputs to be energized, right? Now the question is, which one? And then that question depends on which sensor, depends on this sensor. If this value is on, then a number of steps later, I want this field tube, when the field tube opens, I want this to be energized. Otherwise, I want the other one to be energized, right? Let me rename these. This is the large field, large charge. And this is a small charge. Now, let me open the data table here, just for us to, I did not really reset the data table. And by the way, you need to reset this data table when you reset the simulation, because you see it still remembers from the previous one, even though all the bottles are small, it still remembers from the previous one, previous simulation, okay? Now, when you, this is a recent simulation, you also need to clear all data files. Now, when I open the data table again, and the wizard pops up, you see now that all the values are 0, okay? And these are 0 because by default, the values of the data table are 0, and also that's why this simulation is designed in such a way that all the initially all the bottles are small, okay? Now, I'm going to show you something. Right here, we have the first bit shift left, which is which corresponds to this sensor, and that's what we are interested in right now, because we want to tell the field tube which one to energize. Because like here, LS4 is energized. Now we want to say we want to add another condition right before, you have one condition before each of these to tell that, okay, this is a large one, this is a small one, right? So this is bottle number 4 below this one. And I have bottle number 5, 6, 7, all the way to bottle number 11, right? So the gap between 11 and 4, 11 minus 4 is 7, right? And that's exactly the value that I'm going to need here to specify a condition for it. So the value is going to be as follows. The value is going to be a binary. It's not an output, it's not an input, it's not I, it's not O, it's a B. And we know it's B31, which is this bit shift left. And it's going to be the 7th one, bit shift left, number 7. And that's because like when it senses here, it goes 7 steps later, it goes to this point. So if the value is, if 1 enters this right here, 7 steps later is going to be here. Okay. And this is the value that we, okay, this is the value that we want to tell the PLC to keep track of. Okay. Now I put B37, right? And I'm going to be looking for exactly the same value right here, right? So that is going to be the exact same value. And the difference here is that we said this sensor goes from 0 to 1 when the bottle is large. That's why we say we have examine if closed and we have examine if open, because like we wanted to look for small charges, small bottles, right? So if I want to rename this for you, that would be is large, but I cannot rename it because unfortunately it's going to be, just call it large. So that means if it's large, if it's true, then charge this. If it's not large, then use this one. Okay. Now, if I go ahead and download this, let's now, I think it's a good time for us to download this program and see what we've created. Now, what I would expect from this is that so far the system is on, we have the stop and go movement, and we have the bit shift left. And what we added here was the limit test. Within that time, we want the fill tube to turn on, to be open. And then depending on the size of the bottle, we want to energize one of these charges, right? Now let's go ahead and get started. So you see now the fill tube is energized, and then because the condition back there was small, it's going to fill up the small one, it's going to energize this one. Now we expect this one to be filled up with orange. Now that's successful because, again, if I open the data table here for you, you can keep track of your large bottles and small bottles. And you see, just pay attention to this value. Every time it's 1, we have orange. Every time it's 0, we have blue. 1 orange, 0 blue. This value exactly matches, must exactly match that one. Large, 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 large. Okay, so you get the idea. Now this one is going to be the blue one. Okay. All right. Now there is a problem here, and you see the system really doesn't recognize, doesn't really know whether this is a small bottle or a large bottle. And wizard is back. And sorry about that. Okay, now the next thing we want to do is that we want to follow a very similar logic, right? But in this case, I'm going to use, instead of using B317, I'm going to use the second bit shift because I want to avoid I don't want this to be energized. I don't want field 2 to be energized or any of these to be energized if the bottle is broken, right? And I already know that this is bottle number 4. This is number 5, 6, 7, all the way to 11. 11 minus 6, 5. Okay, so I'm going to say that if this is not broken, so if this is V3, here we're talking about V3, 3, here, and the fifth one, if it's not broken. If it's not broken, then open this, right? It's redundant. I could probably just be, I would probably be fine with this, but like you could also add the same condition here just to be safe as I have it in the slides, but you don't have to. Now, if I download and run this again, you see it should avoid filling up the broken ones. That's another issue, you know, that's the gap between, maybe we need to reduce this gap. This is probably, that's why it broke the bottle. Because as I explained, the system, the beauty of PLC is that it can create complex logic with very rudimentary input, like sensors and actuators. These are simple sensors and actuators. They don't really understand that they have to like wait maybe for a few more milliseconds longer to avoid breaking that bottle, right? And that's our job, to program the PLC in such a way that it avoids this. But you see now, using this one examine if open condition, we have now programmed the PLC to detect, so you can use this sensor information down the line, avoid filling up those broken bottles, because we're going to discard them anyway. And that concludes this step of the process, which is filling up the bottle. The next step for us would be to cap the bottles. Now that we have programmed the PLC to fill up the bottles, we have a couple of tasks left, actually, programming tasks for us. The next thing is that we want to cap the bottles. We want to energize this, activate this cap RAM, and the logic is going to be very similar to what we created. And then we are going to discard the broken bottles and control this divert gate to open and close. But again, all of these operations will be programmed using bit shift left and the values of these two sensors collected using the BSL instructions that we have right here. Okay, the next step for us would be to cap the bottles, right? And then what I want to do is that during this limit, I mean, this is the limit, this is the time during which the this is the time during which the system stops. That's the stop period, but with some cushion here for the system. So during this stop, I want the field to open, right? But I can also use that as like the same input condition with some revised input conditions to also energize the cap RAM. Let me quickly revise this first output here. And I'm going to move this inside the branch because for the cap RAM, we're going to need a different value. First things first, let's again move the output here. And that is going to be cap RAM, right? So we said when it gets to this point, we have 6, right? 5, 6, and this one was 11. 11 minus 6, 5, and that's why we have the fifth one. Again, starting from here, 5 bits down the line. This one, when it gets to this point, it's 21. 21 minus 6 is going to be 15. Again, the same logic. You could like count the number of bottles, but the good thing is that you have the bottle number here, so you can just like subtract them. Again, this is 5, 6, and this is down the line 21. So I want 21 1 minus 6, 15 bottles later, I want the PLC to look for that number. And if that number is not a broken bottle, I want this to energize. If it is a broken bottle, I don't want to cap a broken bottle. And by the way, by the time we program this slot will be empty. So I don't want the cap ramp to just energize when there's no bottle underneath it. Okay. With this very similar logic here, I energize B3, 3, but in this case, I need the number 15. So if you open the data table, that is going to be B33, number 15 right here. We want the PLC to keep looking for that, to then inform the cap RAM that, hey, if it's 1, I don't want you to energize. If it's not 1, then energize during this period. Okay. Similar to capping the bottles, we also want to use, we could use the same logic, again, similarly, during this time period. As I said, we program this stop and go movement to then program multiple things at the same time during that period, right? So the next thing that I want to do is that I also want to add another branch here. Move these inside the branch. And then I want to energize this scrap gate, right? And I want the scrap gate, in this case, I want the scrap gate to open if the bottle is actually broken, right? This was 6. This is 15. So I want 9 steps, 9 bottles down the line again. 15 minus 6. But in this case, I want to use an examine if close because I want the system to actually discard the broken bottles, right? Now, that concludes the programming of the PLC to cap the bottles and also discard the broken bottles. Let's download this program to the PLC and see where we are. You can add an additional condition, like more advanced logic here, because we don't want to cap these pre-existing bottles anyway. You can update that, but for now we're good. You don't need to worry about that, but that could be revised using very simple logic. So in terms of filling up the bottles, we are good. 2 things must happen here with this logic. We skip the broken bottle. The broken bottle must be discarded here. It is discarded. You're capping the bottle successfully, right? You're making progress. And the cap RAM actually skips that because of this condition. Cap RAM skips that slot. So it needs to discard them, and then the cap RAM is not going to be energized here. You see, it's going to skip those 2. And again, this is not, you're not using any vision system, any advanced sensing system. These are very simple limit switches and very simple actuators. And the logic, the intelligence of the system comes from the way you program. Now, you saw in the animation that, and sometimes things like this happen. And that's also another extra, I mean, if you want to explore that further, there are some additional considerations to avoid those like breaking bottles like that. But the next thing that we want to do is that as soon as this bottle is discarded, we really need to start this grinder, because otherwise you see these broken bottles keep making a mess here. And in order to do that, we need to energize the grinder. So far, we've programmed the PLC to do most of the tasks that we really wanted to this bottle line simulation to perform, but there's still a lot of other tasks left to be done. The next thing for us to do is that, as you saw in the animation that I showed, the last animation that I showed, The bottles are discarded, but we really need to energize this grinder every time a bottle is discarded. And as you've probably guessed, I mean, you could use this scrap gate as a condition or the sensor here. I'm going to use the sensor because just to be like consistent with the previous ones. And the sensor here is sensor LS8. So every time that LS8 sensor senses something, which means goes from 0 to 1, that means the scrap gate is open, right? We want to energize the grinder. And we want the grinder to be de-energized right after the scrap gate is closed. But we can also add an additional condition, maybe add some delay to it to like keep grinding for 1 more second and so on. You can add more and more complex logic here, but for now in this simple example, just accept that as a sufficient condition, right? Okay, the next thing we want to do is separating the large and small bottles. And that is using this divert gate right here. Okay. In order to do that, I'm going to, again, everything we said, like we use this stop and go movement and this limit test here. And we want everything to take place here, like similar to what we did for this field tube and for the cap round. We are going to use this interval to open the scrap gate and then move the large bottles to the scrap, to not the scrap gate, the divert gate, and move the large bottles to the divert gate. I'm going to call this divert gate. And in order for this divert gate to work properly, the condition here for us would be that the bottle is large, right? So this is number 4, and this goes all the way number 25. 25 minus 4 is 21, and we said that's why we needed more than 16 bits here. So 21, it goes to it goes all the way here to 15, and then here I need B3 number 5. So I need this one, right? That's the value that I need for my large bottle. So that's the value here that tells us B3 2. Now we have moved to the next one, to the next line, /5. So here with this condition, I'm telling it that this is a large bottle before the divert gate. And I also want to make sure that the divert gate doesn't really open when there was a broken bottle here. It was a large bottle, but the bottle was not broken. If it was broken, there's no point in opening that divert gate. And similar to the other one, again, this was number 6. This is 25. The other one was number 4 and 25. That 21, number 6, 25, 19. We go to the next line, and in that case, it's the bit shift left instruction that was for broken bottles, and now we have moved to the second line, to the second set of 16 bits here. So it's going to be B3 4 /3. So here what I'm telling it again is that the bottle is large and it's not broken, and because of that we want to open this divert conveyor. Now if I go ahead and simulate this, you will see that the divert conveyor we are not energizing. Let me just simulate it for you. If I simulate this, what happens is the system should keep working fine. And let's give it some time to bring a large bottle here. So this condition is not true. This condition for the divert gate is not true. I mean, the bottles are good, but they're not large. I mean, the bottles that used to be here. Now, as soon as the large bottle gets to this point, this condition goes from 0 to 1, and it's going to divert it to the other one, right? But fortunately, this conveyor really needs to move. Otherwise, we're going to end up breaking all the bottles, right? So what I want to do is that I'm going to, simply we want to tell the PLC that if the main conveyor is making those stop and go movement, there's no point for us. There's no need to recreate another timer for this one. We want this conveyor to move in sync with the other conveyor. So what I'm going to do is that I'm going to create a simple condition here and tell the PLC that if the main conveyor is moving, every time that main conveyor moves, I also want you to move this one. I want you to move the divert conveyor, right? Now, if you download quickly and run the PLC, you see the stop and go movements are going to take place here, right? Now, that solves the problem to some extent, but there's no point in moving the conveyor when there's no other large bottle coming. So we want this system to now stop and wait until there's actually a need for it to shift to the right for the next to open up some room for the large bottle, again, just to optimize the process. And that is going to be a very simple and quick fix. So what we're going to tell, like similar to the condition that we specified here, we told the PLC that if B325 is true, which means the bottle right here, if the bottle right here is large and was not broken, right, using like is large, which is B325, and was not broken, B343, right, then open the divert gate, right? Here, I could add the same condition, but shifted one bit to the left, one bit in that case to the right, and add a condition for the PLC. You tell it that, okay, if the previous bottle, if the bottle before this divert conveyor is large and was not broken, then shift this thing to the right, then move the divert conveyor. So the condition here is going to be, again, the same thing, but one bit shifted to, left and right is confusing right now, but like one bit before that. So B324 instead of 25. So instead of this bottle right here, I'm talking about this previous one. And again, B34, in this case, 2 instead of 3. Right? And then what happens is, if I need to reset the simulation probably. And then you need to reset the simulation, and you also need to make sure that you reset the data table, because otherwise it remembers all of those bit values that you've been shifting. Now, if you download this and run it, hopefully it won't take too long, but it should only shift this thing to the right when there is a large bottle coming. And that was not broken. And opening the data table, you see that what data we are interested in. Again, like pay attention to these. It's right here. So when it gets to this point, it's going to shift to the right one, and then not shift it, then shift another one. And it's not shifting until it gets to that point. So that way, we really only move this divert conveyor when it is absolutely necessary for it to move. When we need to open up one spot here for the next bottle coming. Okay, and that's how. And then I encourage you to review these values that we added here. B325, B343, B324, B342. Look for those values and run the simulation and verify that, or pause the simulation and verify, look for those values and verify that the values match what you see on the data table. That would help you better understand binary data format and bit shift left, because this is, again, this is a very important instruction in PLC programming. That concludes the steps associated with moving, with separating the large and small bottles. The next step, which is going to be one of the last steps of this exercise, is going to be associated with this scrap conveyor, because you see the number of bottles here that can be stored, the number of scrap bottles that can be stored in these boxes is limited, and we don't want these boxes to overflow. And we want to program the PLC again to use these very simple limit switches and very simple actuators to move the box away and bring the next box below this grinder. And you see, like, the grinder is now getting very close to being full, and we don't want that to happen. We don't want the box to be overflowing, right? That is going to be the next step of the tutorial that I'm going to show next. The next step of this tutorial is to move the scrap boxes away. So we saw that in the previous video that all right, the next step of the tutorial, which is going to be the last one of the last few steps of this tutorial, is to move the scrap boxes away. We know that we already saw that the scrap boxes have a limited capacity. So we want to count the number of bottles, that number of scrap bottles that are ground and sort of like dumped into these boxes. And then once the box is full, we want to remove the box, bring the next box, the scrap conveyor moves this way, bring the next box, and then continue the process. In order to do this, the very first thing I want to do is to count the number of bottles. That's important because that's the only way for us to know exactly how many bottles have been discarded, and we know that the capacity of these boxes is a function of those bottles, right? Scrap bottles. I'm going to just be consistent with the tutorial. I'm going to create a timer with the address C50 and then the preset value of 12. We can change the number of preset values, but if you run the simulation, you see that it's roughly 12, I believe, and after the 12 it's going to like overflow. And there are different ways to count the number of bottles discarded into this, but what I'm going to do here is to use an input, a simple examine if closed, and use the scrap gate as, or the grinder, it doesn't matter. I mean, I'm going to, just to be consistent, I'm going to use the grinder. So every time the grinder is energized, we're going to count. That means there is a bottle that is being ground and then discarded to the boxes. Okay. Now, what we want to program here is that eventually we want to come up with a logic here that controls the movement of this scrap conveyor. Okay. And what that means is that, again, as I explained it already several times, this system does not contain any intelligent sensing system or camera system, etc. Here we are dealing with very simple limit switches and actuators. Okay, and the logic, the underlying logic, the complex logic really depends on how we use these inputs and outputs and how we put them together, how we formulate this ladder diagram to implement the logic that we desire. In this case, what we want to do is that we want to remove the boxes that are full and then bring the next box that is empty. We only have one limit switch here, LS10, that is going to help us determine the existence of a box. So the logic in simple English, simple, like if you want to sort of like simply explain the logic, is going to be as follows. We want the scrap conveyor to start moving when the box is full. That means the counter is done, right? That's the very first logic that we're going to be implementing here. And the first condition. And the second condition is LS10. The second condition is that LS10 sensor is sensing something, right? So I want the scrap conveyor to then run and continue to run. I need a sealing circuit here. So let's review this condition one more time. We want the scrap conveyor to start moving only when the box is full. Counter is done means the box is full and the box is still here, right? So the box is here, the box is full, start running the conveyor and keep running it until something else happens. And you know, if I'm not going to download and simulate this because you already know that if you run this this diagram, what is going to happen is that as soon as the first box is full, the conveyor will start running, but there's no way for us to stop it, right? Before I program that logic, what I'm going to do is that I'm going to add another mostly like safety caution kind of a condition here that if the scrap gate is not open, I want you to run. If the scrap gate is open, I don't want the conveyor to be moving. I want to always have a box below that. Okay. And that is going to be the condition here for the scrap conveyor to move. But you already know that, again, this is not enough because as soon as we move the conveyor, it's not going to stop until the scrap gate opens, but and we never know what position that might be. I mean, it could be like somewhere in between these boxes. Again, this is a very simple motor, on and off, and we have a very simple limit switch here, and we want to implement that logic here. Now, this is probably one of the most challenging parts of this whole tutorial and all the tutorials covered in this class, including the assignment. And I'm going to implement my own logic. For your assignment, feel free to replicate what I create here, but this is probably a good challenge for you to think about this and to challenge yourself and try to come up with an alternative way of programming this. Now, my approach to this is going to be as follows. I mean, so far we're going to use two auxiliary binary values here, and these values do not have any physical representation. They're nowhere in the system. In order to use that, I mean, the slides I have the bit shift. I have binary values, address B300, B301. I'm going to just like to show you a different that, you know, these are some arbitrary selections. I'm going to use two different values, but again, don't get confused. That's the same thing. Again, like the selection of these values really doesn't matter as long as you don't choose anything from B31 all the way to B34, because we already know that for our BSL, we use those addresses. So make sure not to use the B31 all the way to B34, but anything after that or before that, I'm going to use after. It really doesn't make any difference. These are two placeholder values. So I'm going to be playing with this B35 instead of B30. In the slides, you have B30. I'm going to implement a logic here that is firstly, again, like an explanatory, like a description of the logic that I'm going to implement, that I need to implement. So the logic reads as follows. I only would like this scrap conveyor to move only if the counter is done, which means the box is full, the box is still here, the scrap gate is not open, but I need another condition, right? And then the other condition is that I want the scrap conveyor to keep running, to keep the motor to remain energized through the sealing circuit until the next box is here, right? So I want it to keep running, right? I first am going to just name this next box here. And again, in the slides, I have it as bit A. Until the next box is here. If the next box is not here, keep moving, right? And then the address that I'm going to use is B3, in this case, 5, 1. It's some arbitrary value again, but you need to you need to give this address, and we're going to be using these two bits to basically write those auxiliary values that do not exist. Again, there's nowhere in the system for us to sense that the next box is here. I'm only going to rely on this LS10 sensor and the counter, and you see that it is possible. So that's a creative solution. That's a smart solution to a problem that otherwise would have needed more sensors, more expensive implementations, and so on. Okay, so take this from me from now. Next box is not here. So this line, the logic here is correct now. Like if the box is full, the box is still here, and the scrap gate is not open, keep running the conveyor for as long as the next box is not here. But once the next box is here, this is no longer false, this is true, so it's going to stop the scrap conveyor and the process is going to continue, right? Now, the question is, how do we program this? How do we program next box here? And in order to do that, I'm going to need another auxiliary value, which is going to be, I'm first going to program it as an output. I don't know what happened here. I'm first going to program it as an output, and the output is previous box is gone, right? So the condition is as follows, right? If the scrap conveyor here, if the scrap conveyor is running, right? The LS sensor is not sensing anything, right? So again, I'm implementing my logic in a very simple, like understandable, like language that that goes as follows, like, and then I'm going to give it this an address. So let's first give it the address B350. So make sure not to overwrite things on top of each other, but again, B350 is going to be this. So I'm borrowing these two bits from this address that is not being used anywhere in my program, right? So the logic reads as follows. The logic reads E350. What we're saying here is that, and I also have another input here to add, which is E35. May sound a little bit confusing, but it actually is not. Let me explain it to you. All right. So what we're telling it that the PLC right now is that, I mean, the logic so far should make sense. Again, I'm going to repeat the main one. If the box is full, counter is up, and the sensor is sensing something, the scrap gate is not open, and the next box is not here, keep running the conveyor, right? So remove this box. The next line says that if the scrap conveyor is now moving, right, the LS sensor is not sensing anything. right? So the conveyor moves this way. So if the conveyor is moving, the L sensor is not sensing anything, right? And the next box is still not here. That means we're in this middle area. So the previous box is gone, but the next one, new box has not arrived yet, right? Then energize previous box gone and keep it energized, keep it true until the next box is here, right? And then that is going to be the next one. Then I'm going to create a next rung and say, what are the conditions that the next box is here, right? What are the conditions that this becomes true? And now I'm going to change that as an output, right? Next box is here, right? And this previous box gone, by the way, this is in my slides, this is okay. Now the condition reads as follows. If the previous box is gone, right? Now, what I'm telling the PLC now is that previous box is gone. Now, we are in this middle area. If the previous box is gone and now the LS10 sensor senses something, right? What does that mean? That means there is a new box. That means the next box is here, right? And I'm going to keep that true. So the next box is here for as long as the previous box is gone, and I want to seal it in, right? Until the scrap conveyor then stops. And as soon as the scrap conveyor stops, this becomes false, and then everything is reset back to where it was. So that completes the cycle. So let's read this again, and then I'll try to explain it so it makes sense. But again, this is my way of programming this. You could do it your own way. First, we count the number of bottles, and I'm going to reduce that to a small number so we can simulate and see it in action. The very first thing is that these are all the conditions that I'm giving the PLC to know when to start and stop the conveyor, right? The first three ones are actually common sense. If the boxes are full, if the box is still here and the scrap gate is not open, keep running it. But the other condition is that if the next box is not here, the previous box is gone, the next box is not here, right? Now, in order to program that, the condition is that the previous box is gone. That's the condition that I need. If the previous box is gone and the LS sensor senses something, that means the next box is here, right? But if the LS10 sensor is sensing something and the previous box is not gone, that means the LS10 sensor is actually sensing the current box, right? So that's the condition here for my next box is here, or bit A, to be true, right? And when the next box is not true, for that like time in between, that the conveyor is running, the LS10 sensor is not sensing anything, right? And the next box is not here yet, right? I want this to be on, right? And then that being on, and then LS10 sensor sensing something, that means the next box is here that is going to stop, right? And as soon as that stops, everything is going to get reset, right? Because this was already reset, because as soon as this is true, this is false, and then this is going to be like turned negative, and then turn 0, like go false, and then the cycle will continue. I let you, like, please spend some time thinking about it. Don't just like create and run the simulation. But now I'm going to run the simulation, and then if there's no error here in the implementation of things, that should work. But I encourage you to do it your own way, try to implement it in different forms, and then see if you can come up with another. And in case you came up with a better solution, an easier solution, please share that with me. I'm curious to see if there's any other way. I would be glad to see that. We just discarded the first bottle. We should wait for 2 more bottles here. It seems like the program, we're almost done. And then the last thing that we are going to do, and I'm going to show it for one of these displays, is going to be displaying, counting the number of boxes. But now let's first wait and see if the program works. Now, remember that I've reduced this to 3. So as soon as the next bottle is discarded, the system should remove this box and bring the next box. But it didn't. Something is wrong here, and let's find out. Now you see that the conveyor doesn't even stop. So what we have missed here is, first of all, I'm going to add another condition here, and that is going to be, is the system running or not? If the system is not running, I don't want the conveyor to do anything, right? Now let's review and see what could have potentially gone wrong here. I did not reset the counter, right? So this is the step. I have it in the slides. I did not reset the counter. This is not in the slides, may not necessarily be important for you because the system is going to, the conveyor is going to be stopped most of the time. But make sure to add this. In case you didn't add it, that is going to be fine. That is not going to break the system. But one thing that I did not do is that the counter is now done and it's going to be like remain done. So what I'm going to do is that as soon as the next box is here, that means the next box is empty, right? So we want to reset the counter. And in order to do that, we do C50, and that is going to reset my counter. Now let's reset the simulation, reset timers and counters, clear all the data files, then make sure to download it to your PLC. Now let's run the simulation one more time, and hopefully this time things will work. Now it's working perfectly fine. The final step is to count the number of bottles, the number of large bottles, small bottles, and broken ones, and then project them on these screens. I'm going to do it in this video. I'm going to do it for just one of those screens, and if you do it for just one of them for your assignment, that should be fine. But in the slides, we have it for all of them. Now, let's say, for example, we want to count the number of large bottles in the system, right? And then similarly, you can do the same thing for small bottles. Now, it could be like every time I need a counter, first of all, and we need to use a different address for the counter. Again, this is an example of having multiple counters in the system at the same time. And let's give it a large number, a large preset number. And here we are going to be counting the number of boxes. I don't want previous box count, actually. I want the number of the bottles, sorry. I could use LS5, or I could use the number of times that the large charge was energized. And that way, I should be able to count every time the large charge is energized. I should be able to count the number of large bottles in the system, right? And And in addition to that, I also would like to, every time I sense, I count the large field, the large charge is energized, I also would like to energize another output. And that other output is going to be this screen, right? This value associated with the large screen. If I click on this screen, it shows me the value. I want to energize that. And I'm going to rename that as the large LED display. So every time I, again, I fill up a large bottle, I'm going to count the number of bottles, and I'm going to also communicate that data with a large LED here for this one. And then one thing that we need to do here is that we need to do some conversion here. And the conversion goes as follows. Now I know that like every time I energize this LED, what I need to do is that I need to convert that value to decimal. And in order to do that, I go to my math, compute and math instructions. And all I need to do is that I need to take a source value, and the source value in this case is the accumulator value of my timer, my counter. And then I want to write this to the output in this case, which is output number 4. If I open the data table and go to outputs, it's output 4, and then each of those, like output 212, the other one output 211. Each of these values is a binary value, and what we want to do is that we want to convert that to a decimal value for this output for this screen to understand it. So we're basically taking that binary, that integer value, and converting it to decimal. Okay, the integer value is the accumulator value of the counter. Now, if I download this and run it, now it's going to, again, I need not reset the simulation. I need not reset the timer and counter. And this is actually a good example for you to see that, if you don't reset it, the system still memorizes, the simulator still memorizes those previous values. So you probably want to do that before each of your simulations. Otherwise, it's going to assume that there were like large bottles here, etc. And that concludes the tutorial. So now we have programmed the PLC to run the bottle line simulator. And again, like the only thing that I'm counting right now is the large bottle. So as soon as the first bottle gets to this point and gets filled up, it's going to count it. We are going to be counting the number of large bottles. The simulator runs. So we have a stop and go movements. We've used several simple limit switches and several simple actuators to run this system in a stop and go movement, detect the existence of the bottles, the size of the bottles, and the condition, whether they're good or bad or broken. And then we skip the broken ones, we discard the broken ones to these boxes and grind them and discard them to the boxes. We cap the good ones that have been filled. I mean, we fill them up with the correct type of liquid here. And we also program this divert conveyor to move and sort of like to separate the small bottles from the large ones. And we also program this scrap conveyor to remove the scrap boxes once they're full. Again, I reduced it to 3, but you can leave it, move it up to 12. And lastly, we programmed this LED screen to count the number of large bottles. You can also count the number of small bottles and the scrap ones in a similar format. And for some reason, some part of the logic doesn't seem to be working. Let's rerun the simulation again. If you ran into that issue of the conveyor not moving properly, let me know. But this should work. I'm not sure why that error happened. I need to reset simulation. Also reset the timers and counters and clear all the data. Make sure to do that again, to do all of these, to reset everything before you run it. Verify that your timer is correct, your counters, you have the right value here, and then it should be good to go. Okay, that concludes today's tutorial. Please follow the same instructions and try to perform it. And if you have any questions, if you run into any issues, feel free to contact me. For your assignment, I want you to basically recreate this tutorial yourselves. And again, I encourage you to try it your own way, to try doing it in a different, like programming the logic in different ways, and then let me know in case you came up with some other, maybe more efficient, more creative ideas to program this tutorial. That concludes today's session. Thank you very much. I went a little bit over time, but I thought I believe that was necessary to provide you with all the details and instructions that needed to complete this tutorial. This concludes our module E. The next module and the last session, the next module is going to be manufacturing execution system, and we only have one session left. I see you after Thanksgiving. I hope you all have a happy Thanksgiving break. I'll see you after the Thanksgiving break. Thank you.